Okay, class, howdy. It's supposed to be Monday, February 24th. Probably where I am, it's Tuesday already. But we're going to continue on with the lectures, and today's lecture is a follow-up on last Wednesday's lecture on op-amps. Today we're going to talk about common circuits. Now, before I get started in the lecture, one thing I want to remind you of is that you need to remember the configurations of these op-amp circuits. I think I showed you just one last time, which is a voltage follower. You need to know what that looks like. I'm going to show you about 5 or 6 more today, and that'll probably be all the ones I'm going to show you. But you need to remember, you need to memorize what these op-amp circuit configurations look like and what they do. Basically, you've got, as you have with the voltage divider, you've got a gain term. So you've got an output divided by your input is equal to some term that you've calculated through use of impedances and resistances and so forth. That's also going to be true with op-amp circuits, and you'll do a couple of those calculations in homework, but ultimately at the end of the day you need to remember for these specific circuits what those gain terms are. So let's go ahead and start on this lecture. This is op-amps common circuits. And I'm going to start just by finishing up a little bit on the KA741 op-amp last time, some stuff off the data sheet. The VCC pin, the input voltage is specified at max 15 volts. The negative power supply, V sub E, is specified at minus 15 volts max. All these at ambient temperature of 25 degrees C. The input parameters, the input offset voltage is 2 volts. That is the voltage that must be applied to an input pin to give the zero output voltage. And remember, we talked about this when we were looking at the op-amp configuration. For an ideal op-amp, the output offset voltage is 0. The input bias current is 80 nanoamps, and that is the average of currents flowing into both inputs. Ideally, both input bias currents are equal. Remember also the golden rule of op-amp says no current is flowing in to the op-amp, so this is just a real world specification of the op-amp, but the way that we analyze these says no current is flowing. And bear in mind here also that 80 nanoamps is very small. That's 80 times 10 to the minus 9 amps, so that would be 0.08 microamps, extremely small current. The input current, the input offset current is 20 nanoamps. That's the difference between the input bias currents when the output voltage is 0. The input voltage range is plus or minus 13 volts. That's on the 2 input terminals. That is the range of the common mode input voltage. In other words, the voltage that's common to both inputs and ground. The input resistance, 2 megohms. When you have the positive power supply voltage at plus or minus 20 volts. Okay, so 2 megohm resistor max. That's the resistance at either input with the other input grounded. Output parameters. The output resistance is 70 ohms at frequency of 1 kilohertz. Now that's pretty small resistance, and what we like is for it to have a very large or infinite input resistance and a very small output resistance. So that is in essence the resistance of the op-amp looking back into the output. At the input frequency of about 100 kilohertz, it begins to rise dramatically. So really above 100 kilohertz you begin, or at 100 kilohertz you begin to have problems, much higher output resistance. The output short circuit current, 25 milliamps. That's the maximum output current that the op-amp can deliver to a load. The output voltage swing, plus or minus 14 volts. And that's with the resistance of greater than or equal to 10 kilo ohms. So depending on the load resistance, this is the maximum or the peak output voltage that the op-amp can supply without saturation. Dynamic parameters. Large signal voltage gain. 200 volts per millivolt. Okay, that's quite large. That's 200 times 1,000. That's 200,000 gain. That's at a voltage of plus or minus 10 volts for power. So that's the ratio of the maximum voltage swing to change in input voltage required to drive the output from 0 to a specified voltage. The slew rate is 0.5 volts per second. That is the time rate of change of the output voltage for an op-amp circuit with a voltage gain of 1. Okay, so that means that your resistors on the outside in an inverting op-amp circuit would be equal, so that you'd have a gain of 1. A few other parameters. Supply current 1.5 milliamps. That's the current that the op-amp will draw from the power supply. Common mode rejection ratio is 90 decibels. So what that means is that's the measure of the op-amp's ability to reject signals that are simultaneously present at both inputs. So if you've got voltage inputs coming in on the inverting and non-inverting terminals, and they're carrying a noise signal on both of them, the op-amp can reduce that noise, that's called common mode noise, to a factor of 90 decibels, which is an extremely great reduction in that noise signal. So the schematic of what that op-amp looks like on the inside, and I'm not going to go into any detail on this, but so you've got your non-inverting input here, your offset null here, your negative power supply voltage here, your positive power supply voltage here, your output here, another offset null here, your inverting input here. What else is in here? A lot of transistors and a lot of resistors, and the resistors are numbered, R12, R11, so forth. The transistors are numbered Q17, Q16, etc. So it's pins and transistors and resistors, and that's pretty much it. This is what they used to look like. So let me go back and compare just very quickly the picture. I hope it's not only in the last lecture, but I'm sorry. I'm afraid it is in the last lecture only. So let's go back. This is what op-amps used to look like when we made them out of vacuum tubes. Big, bulky. They worked pretty well, but not as reliable, not as rugged, not as cheap, not as power efficient. So what we have today is much, much better. Again, two golden rules of op-amps. The output will always change to make the voltages at both input terminals equal. No current enters the op-amp. All right, we already showed you this one. The voltage follower causes the output to provide negative feedback to the input. And I think we already kind of looked at this. Because of Rule 1, output will match the input on the non-inverting terminal. Because of Rule 2, no current flows at either terminal. And we'll just move on. Okay, so that's a voltage follower. You should know what that looks like, what it does. This is the first other op-amp circuit. It's called an inverting op-amp. Let's look at it a little bit. Remember, you don't have your input power lines here. You just have your two input terminals and your one output terminal. So here, your non-inverting input is connected to ground. Your inverting input is connected to some input voltage through a resistor R1. And it is also connected to the output. There's a feedback line here that runs through resistor R2. And think about just for a moment what effect these values of R1 and R2 might have on this circuit. So I'm going to let you think about that just for a moment, and then I'm going to follow up by talking about it. So to give you a little hint, remember that in all the circuits we're dealing with, we're looking at what the gain is for the output of the particular circuit configuration compared to what the input is. And you'll find as we go through this that these two resistors go a long way in determining what the gain of this op-amp will be. So that in terms of comparing your output voltage to your input voltage. All right. So the inverting op amp is the second most basic of op amp circuits after the voltage follower. The first golden rule of op amps states that the output voltage, this one right here, will change to equalize the voltages between the input terminals. And in this case, it's doing it through this feedback right here. It's providing feedback to try to force these two input values to be the same. Since the non-inverting input is grounded, we'll call that voltage equal to 0. That means that we can assume for purposes of calculation that the inverting input voltage right here is also 0. Kirchhoff's law states that the sum of current flowing into and out of node 1, and this is node 1 right here, must equal 0, right? And the second golden rule states that no current is flowing into the op amp. So if you look at the three directions that lead into or out of node 1, you know that this one is 0. So if we look at it a little bit bigger, we can say that I1, we'll call I1 right here and I2 right here, both of them going into the node. I1 plus I2 is equal to 0. So that's something that we can state based on the laws that we have. What is I1? Well, it is V1 minus 0, because 0, the voltage here has to be 0 because the op amp rule says it has to be. Vn minus 0 divided by R1. That's what our I1 is. So for I2, we have V out minus 0, because again the voltage here is 0, divided by R2. Set those equal to 0. This condenses down into Vn over R1 equals minus V out over R2, and ultimately we solve for V out, and we find that the gain is a negative R2 over R1. And this negative sign is why we call this an inverting op amp, because it inverts the signal, and the magnitude of the gain is defined completely by the values of these two resistors, R2 over R1. So if you want to have a large gain, then you put a resistor R2 that's much larger than R1. Bear in mind that these op amps, and if you'll go back and look at the slides on the specifications of the KA741, they have maximum gain possibilities, okay? So if you wanted to put a 10 megohm resistor here and a 0.1 ohm resistor here, you would exceed the capability of this op amp to produce gain. So that is something you have to keep in mind. Okay, so here's our non-inverting op amp. This is the third one that I've shown you. We've seen the voltage follower, the inverting op amp, and now the non-inverting. And why we call, well, one reason we call it a non-inverting is because the voltage in is coming into the non-inverting input. Note also that the inverting input is connected to ground through a resistor. And there's also feedback again from the output voltage back to the inverting input through resistor R2. So it's kind of a similar circuit, but there are some differences, and you need to remember what this is and that it's a non-inverting op amp. So in this case, V out is equal to V in times 1 plus R2 over R1. So the gain term in a non-inverting op amp is very similar, but it's got a 1 added into the gain term, and there's no negative sign in front of it like there was in the inverting op amp. I'm going to give you figuring this out as a homework problem, and you can work it similarly to how we did the circuit analysis on the inverting op amp. So we've looked at 3. This is number 4, differential op amp. It's a little more complicated, but we use the same 3 basics: golden rules of op amps, Ohm's law, Kirchhoff's laws. So let me back up here just for a moment. Let's look at the circuit itself. In this case, we've got 2 different voltage inputs. One of them is connected to the inverting input through a resistor R1. The other one, V2, is connected to the non-inverting input through a resistor R1. And R1 is connected to ground through a resistor R2. And the output voltage is connected to the inverting input through a resistor R2. Note that R2 are exactly the same resistance values. R1 and R1 are exactly the same resistance values. So how do we solve this? V at node 2. Let's look at the voltage at node 2. It's equal to V2 times R2 right here over R1 plus R2. And how do we get that? It's basically the voltage between node 2 and ground around resistor 2. Remember, it starts to look like a voltage divider, right? This is our like our voltmeter resistor here, resistance here, and this is our input resistance. So this is our gain, R2 over R1 plus R2. We also know that that has to be equal to V1, right? Because V2 and V1 have to be the same. Sorry, not V1, but the voltage at node 1 and the voltage at node 2 have to be the same because the golden rule of op amp states that they do. So let's look at what V1 is. V1 minus the voltage at node 1 over R1, that is this current right here, plus this current right here, which we can say is V out minus V at node 1 divided by R2 equals 0 because we know there's no current going into this inverting terminal here. So we can do a little bit of rearranging. V1 over R1 plus V out over R2 is equal to V at node 1 Okay, I had to take a little pause there. I'm going to try to get back to where I was in this derivation of our gain term for a differential op amp. So we were using, let's see, I'm losing my cursor here. Hopefully it'll come back to me in just a moment. Differential op amp, here we go. Well, maybe that's not going to work. I'll try a pin out here. Maybe that'll do better. Okay, so I'll just try to start from the beginning. Here we had the voltage at node 2 right here, and the pin is not working either. So now my cursor is working, so that's maybe a better sign. Let's see. Okay, the differential op amp. The voltage at node 2 is equal to V2 divided by, times R2 over R1 plus R2. We know that because this is a voltage divider, and voltage at node 2 between it and ground is just the voltage around this resistor right here, and that looks like a voltage divider, and so that gives us that first equation. We also know that it has to be the same as the voltage at node 1 because the golden rule of op amp says that these are going to be forced to the same voltage. Now, what we're looking at is Kirchhoff's current law. We can define I1 here coming into node 1 and I2 here coming into node 1 and I3 here going out of node 1. We know that I3 has to be 0 because of one of the golden rules of op amps. And that means that I1 plus I2 is equal to 0. We can further say that I1 here is equal to V1 divided by, V1 minus the voltage at node 1 divided by R1, which is what we have here. And then I2 is right here. So plus V out minus the voltage at node 1 divided by R2, and we set that all up equal to 0. Now, we're going to do a little bit of just manipulation of position of terms here. We're taking the voltage at node 1 terms here and putting them over here. Okay, that's all we've done. Vn1 here, Vn1 here, and the two fractions come out to this side. Okay, note further that we've got V in 1 here, V at node 1 here, and we've also got it here. And we can substitute for V at node 1 this term here, V2, and that's a little bit screwy. That was one of the things I was having difficulty with. That's a 2 volt, V2 times R2 over R1 plus R2. We substitute all of that in for voltage at node 1. And then we reconfigure this term 1 over R1 plus 1 over R2 to be this. This parenthetical term and this parenthetical term are the same, okay? When we work all this through, multiply these together, we end up with V2 over R1, okay? So that says that V1 over R1 plus V out over R2 is equal to V2 over R1. And then we solve all that for V out, and we get V out is equal to R2 times V2 over R1 minus V1 over R2. If we pull our R1 out, we get V out is equal to R2 over R1 times V2 minus V1. So what we're measuring in V out here is the difference between these two voltages, V2 minus V1, and note that the minus sign is in front of the one that's connected to the inverting terminal. Note also that our gain term is made up by R2 over R1. And one other point of note is that these R2s have to be identical and these R1s have to be identical. But if those are all true, as should be for a differential op-amp, then it's a very simple outcome. V out is equal to R2 over R1 times V2 minus V1. So another circuit to remember. Now let's move on. Here's a summing op-amp, another very important op-amp. This is your equation ultimately. It looks a little complicated, but it's not. Okay, you've got 3 inputs. They're all connected to the inverting op-amp. The non-inverting, sorry, I keep saying op-amp when I mean input terminal. They're all connected to the inverting input. The non-inverting input is connected to ground. And again, we've got feedback from V out into the inverting terminal through a resistor R sub F. Okay, R sub F means a reference resistor. Each one of these is connected to the inverting terminal through its own resistance, R1, R2, R3. And the output here, and I'll leave this derivation as an exercise, the output is equal to minus, because everything's coming into the inverting terminal, V1 times RF over R1. So your gain for V1 is RF over R1. Your gain for V2 is RF over R2. Your gain for V3 is RF over R3. So basically you're summing these signals, but you can have a different gain for each one if you like by varying the levels of these resistors. But commonly we may, for example, we may be taking a measurement of temperature on a surface, and we don't think that taking temperature at one spot on that surface gives a good representation of what the temperature of the whole object is. So we put out 3 temperature transducers, and we make R1, R2, and R3 equivalent. And so in that case, we're taking an average of those three temperature values, and we're getting an average temperature out. This would be an average voltage from each one of the transducers. Of course, you need to know what your reference voltage is, and of course you need to account for the negative sign in front of this on the inverting terminal. But it's a nice summing op-amp, and it's not limited to 3. You can put more than that, as many inputs as you need. Again, the output is inverted, so you may want to use a voltage inverter to return the voltage to its right sign. And that would be the one that we considered right after the voltage follower, where you just put the input into the inverting terminal and the non-inverting terminal is connected to ground. Okay, we have a couple more to look at. This one is called an integrating op-amp, and it looks like an inverting op-amp, kind of, sort of, except that we've got a capacitor here in place of R2. We've got one resistor, one capacitor. The non-inverting input is connected to ground, and V out in this case is equal to minus 1 over RC, and the minus is because it's on the inverting terminal. 1 over RC, RC becomes the gain term, times the integral of Vn dt plus some constant. Okay, so it integrates this over some time. So an integrating op-amp works quite well as a filter. Okay, if you have a lot of noise in your signal, a lot of high frequency noise, and you want to filter that out and get a smoother signal, this kind of integrating op-amp can work quite well. The differentiating op-amp is almost identical to the integrating op-amp, except the resistor and the capacitor are switched in position. And the transfer function for this is V out is equal to minus RC. Again, RC is the gain term, and there's a minus sign because input is coming into the inverting terminal, times the derivative of the voltage input with respect to time. So basically you're getting the slope, okay? You're getting a gain times the slope of the change in voltage. Differentiating op-amp. So let's go back very quickly. I'm just going to go all the way out and see if I can look real quickly at all the different op-amp configurations we've looked at in this lecture. Okay, let's see. We had, the first one was a voltage follower. Okay, it does not invert, just a voltage follower. Why would you use a voltage follower, by the way? Why would you just not go directly with this voltage as the output voltage? Because essentially you get output is equivalent to the input. Anybody know? I'm sure I can't hear you, so I'm going to tell you. The reason that you use this is because of the impedance characteristics of the op-amp. Okay, with the op-amp you get tremendous impedance at the input and very small impedance at the output, which means that this op-amp voltage follower will give you a very good representation of Vn and not have a great effect on the signal anywhere else in the circuit. Okay, so voltage follower. Again, 2 golden rules of op-amps. Remember, make sure that you know those. You've got an inverting op-amp, and its output looks like this. You've got a non-inverting op-amp, and its output looks like that. You've got a differential op-amp, and its output looks like this. You've got a summing op-amp, and its output looks like this. Don't forget about the minus sign in front. You've got an integrating op-amp that looks like this, and again, minus sign in front, and a differentiating op-amp with a minus sign in front looks like this. Okay, you should know all those, know how they're configured, and know what their outputs are. And that will be the end of today's lecture. Everybody go and have a great day, and be back in on Wednesday.